Thank you very much for inviting me to give this contribution on how to not make just any planet, but a habitable one, illustrated here, of course, by our own habitable planet, the Earth. But I actually want to start this contribution where, sort of in continuity with the previous one, with looking up on the Milky Way together, or looking up on the night sky as it is supposed to be. Unfortunately, this is a sight that has been lost to most people today. And in losing that, we have lost a source of beauty that really is supposed to be common to all. They're a common good if there ever was one. I think we have also we're also at the risk of losing what could be a really important source of community, of communion with one another. I think it's almost impossible to look up on the sky without feeling a source of, like, a sense of gratitude for the universe that we have been given, and that is something that can really bring us together. And I think this is something that astronomy can help remind us of, just how important it is to have access to the night sky, and the importance of preserving the few places where we can still see it, and if possible, restore access to it in all other places. Now, astronomy in some sense begins by looking up at the stars in wonder, and the kind of, I think, wonder is just natural and very intuitive to feel, and then try to translate some of that wonder into scientific questions. And the question that I want to talk about is how you end up forming planets around these stars. And there are two motivations for this. One is that, as Evina just mentioned, is that we now know that basically all stars are worlds of their own, have planetary systems. And I think one cannot help but wonder if any of these systems are looking back at us, and therefore just how many habitable planets there are in our galaxy. But the other one is also to understand our own planet, the Earth. We are a habitable planet, so understanding how to making ones is also trying to understand where we come from and how the Earth fits into the overall sort of cosmic ecosystem of stars and planets. There's a sort of two-tiered definition of what a habitable planet is. One is a more astronomical one, which simple is that you take a planet that has roughly the right composition. It's mostly rock and metal, and you place it at a distance from its star such that it's temperate. It's neither too hot nor too cold. And what it's not too hot or not too cold for is having liquid water. But of course, it's not very, very useful to get the right temperature for liquid water if you don't have any water in the first place. So the second set of criteria I would call astrochemical. So this is where chemistry and astronomy comes together. And that is how often these habitable zone planets end up being dry versus wet, having access to water. But then also, water is not all you need to get going with an organism of life. The second big ingredient you need are chemical ingredients, organics of different kinds. So then the second part of this set of criteria is how often you form planets with access to organics. So water and organics, how often do we end up having those when we make a planet? To answer that question, we need to go to the places where stars and planets form. This beautiful image from the James Webb Space Telescope was released quite recently. It's showing an interstellar cloud, which is where stars and planets form. And as a side note, I don't think it is an accident with our universe that beauty and the search of truth often go together, and I think this is just one example of that. And another thing that I think astronomy helps doing in its search for truths about our universe is also revealing new beautiful structures, as this one shown here. So these clouds, or parts of these clouds, can collapse under their own gravity to form a star, or first a protostar and then a mature star. And because these clouds always have a bit of spin, you will also form a disk around these stars to preserve the angular momentum. Within these disks, you can form many kinds of planets, but if you focus in on Earth-like planets, that forms is a multi-step process where I've tried to color code things that are white or gray that are rocky and things that are more water-like here as blue. So you start forming an Earth-like planet by having some of the dust in this disk that we saw in the previous figure coalesce to form a rocky core. So that's the bulk of a planet like Earth. Most of this is going to be dry, but you could have a little bit of water if there is indeed water in the disk, also in this solid building block. Then you can accrete an atmosphere from the gas in the disk. And again, if there's water there, you could get some water or organics through this accretion of this primary atmosphere, which in the Earth's case was actually mostly lost. And then the third step of forming an Earth-like planet is to have impacts from comets and asteroid-like bodies that also, if there is water and organics around, can be a third way of getting these building blocks of life to a planet. We have entered a wonderful era for thinking about planet formation in that we have this new telescope, ALMA, in Chile, which is an international collaboration between Chile, Japan, Taiwan, Europe, and North America, which allows us to directly observe these disks where planets are forming. So on this next slide, what I'm showing you are astronomical images taken at microwave lengths, so millimeter-sized electromagnetic waves, that shows what these disks are really like. And what you can see is that these disks are not uniform, but they have these sort of dark lanes or gaps in them. And they are there because planets are forming right now, accreting some of the material in this disk. We can actually see planets being made in real time, which is just a wonderful development. So how often do these disks and these planet-forming disks have water in them? We think water is going to be very common in this. First of all, because we can observe water in our galaxy, especially in these interstellar clouds. Water turns out to be one of the most abundant molecules there is in our galaxy, and especially in these star and planet-forming clouds. We have good reasons to think that this water survives the formation of distant planets. One of these pieces of evidence is coming from our own solar system. So if we look at the water here on Earth or in comets, what we find is that there's too much heavy water there compared to what you would expect if the water was made locally. And the best way we can explain this excess of heavy water is that we have inherited it from the interstellar cloud, which are very cold and therefore prone to adding sort of excess deuterium to the water as it's being made. The other piece of evidence we have comes from observing disks directly, especially at infrared wavelengths. When we peer in towards the center of these planet-forming disks, we can look for spectra of water. So what's shown here is in the top panel is an actual spectra towards a protoplanetary disk, and in the bottom is a model. And what these spectra are showing is that water is very abundant in the water vapor is very abundant in the innermost parts of this. So we then have evidence that we should frequently have a lot of water vapor that could go into a planet's atmosphere. And we also very likely have a lot of water in ice form in the outer parts of this disk. That's why we have icy comets in our own solar system. And that planets in general very likely form in water-rich environments. Actually, for planetary habitability, there may most of the time be too much rather than too little water around. So for forming an Earth-like planet, you actually only want a little bit of water. About a per mil of the mass of the Earth is water. And we see enough water in this disk that it might be more common to accrete enough water to form something like a small Neptune-sized planet in the habitable zone rather than a habitable one. And this is one of these open questions that we have in astronomy, how often you end up actually forming sort of the right kind of fine-tuned habitable planet versus a too water-poor, too water-rich one. But water is definitely there, and it's abundant. The second question then is how often you also get organics, and especially the right kind of organic molecules on a planet that's, as it's forming. And once again, I return to ALMA, which cannot just take images of what these disks look like, but also take images of where certain molecules are in this disk using rotational spectroscopy. So on this slide where I'm showing are images of where specific molecules are located in different disks. So where you see brighter emission, there's more of a certain molecule. Where you see fainter one, there's less. I think this is easier to see if I just zoom in on a few, which is what's shown here. So 5 different disks where we have isolated the light or microwaves coming from one organic molecule that is hydrogen cyanide. Now, hydrogen cyanide is not a very good molecule to be around if you are advanced life forms such as ourselves, but it turns out to be a very good one to get the chemistry going, to get you towards the origins of life chemistry. So it's quite exciting that this is one of the organic molecules we see a lot of in this disk. What it's also telling us is that there is a lot of organic molecules forming in this disk as planets are being made. You can see that there is some structure in these disks, and if I were to superimpose some of the previous images I've shown of where planets are carving out these dark lanes, you would actually see that a lot of the bright emission here is coming from exactly where planets are currently forming. In addition to this sort of disk-produced organic chemistry, we also have good evidence that some of the organic chemistry that happens in interstellar clouds, together with a water formation, also survives this star and planet formation process and ends up in the disk. And this chemistry, organic chemistry, is quite distinct from the one that we observe in the disks that are being made in the disks themselves. So when we put that together, what we find is that planets form typically in disks that are rich in organic molecules. What is currently, I would say, less clear, or where like so many of the sort of open questions are, is, well, if a planet is forming surrounded by water and organic molecules, how often do those molecules actually make it onto the surface of the planet? We know that they survive this journey from the interstellar cloud to the disk. How often do they also survive going from the disk into the planet? In the case of water, we have good evidence from the solar system that it does frequently survive. I mean, we see water here on Earth. We actually see it on most planets in the solar system. Most organic molecules tend to be a bit more fragile and may therefore have a harder time surviving the planet formation process, including these impacts that can bring organics to the surface of a planet. So we are pretty far when it comes to our understanding of how to make a habitable planet, but we're definitely not all the way there yet. Still, if we are to sort of try to bring these things together, one of the things that we have learned from the past couple of decades is that exoplanets of any kind are incredibly common. And the kind of planets that reside in the habitable zone, sort of the right temperature, right size, seems to be quite common as well. So we should have many billions of those in our galaxy alone. What we have learned from using these millimeter wave telescopes like ALMA and infrared telescopes like Spitzer, and we also started to use the James Webb telescope for this, is that these disks are full of water and organic molecules. But as I said, how often these habitable zone planets in these environments manage to accrete the right amount of water and organics is something that remains to be seen. And it's also important to remember that just because a planet is potentially habitable doesn't mean that it is going to become inhabited. Between 3.5 and 4 billion years ago, our own home planet made this transition from habitable to inhabited. It is one of the big scientific mysteries, how life originated here on Earth. And therefore, we don't yet know how often we should expect it on other planets. But whether inhabited planets are common or not, I think astronomy helps us also to remind us how precious our own planet is, our own home planet, the Earth. I think there's one or few things that can compete with the wonder that we get from looking up at the stars is actually looking back onto the Earth from space. And that's what I would like to finish. So thank you.
Very much, Karin, for this beautiful talk and bringing us down back to Earth, literally, and maybe showing how precious and how special our Earth could be, or maybe not. We don't know yet how that is. Again, before we go into the general discussion, we have maybe one or two very quick comments and questions. Yes, quick comments and quick answers, please. Yes, thank you.
Dr. Oberg, for your very nice presentation. Could you please say a few words about the possible habitability of exomoons? Would you use the same criteria to define the habitability of an exoplanet with moons, or there would be additional ones? Thank you.
Thank you for that question, which allows me to bring up one of my favorite topics, which is that there might be other habitable places in the solar system, which are not planets. That is, some of the moons around Jupiter and Saturn. So the reason they might be habitable is that they have oceans that have organics in them that are subterranean. So they don't need to be in this habitable zone to have that. The only reason you need to be in the habitable zone is to have surface water. So this would be true also for exoplanetary systems, that you could definitely have moons that are not in the habitable zone, but have these subterranean oceans. The problem is that we don't know how we could possibly detect them, or detect that they're habitable. In our solar system, we can send missions to either drill down or collect some of the geyser material that's coming out of these icy moons, but we cannot do that remotely. So that's why, as sort of astronomers, we have to focus on these habitable zone planets that could sustain surface water.